Hello and a warm welcome. I am Armin Trost, Professor for Organizational Behavior at the Furtwangen University in Germany, and this is my course on social research methods. So, welcome everybody. Today we're going to start with statistics. The most simple statistic you can imagine. Descriptive statistic, univariate statistic. It's basically the statistic we use to describe one single variable, or to be more precise, the values of one single variable. Let me start with how things always start. When you analyze data statistically, you always have a raw data matrix. A raw data matrix. That's what you have. And there is a convention, it's a worldwide convention, I would say, that raw data matrix have a specific shape. And you better learn right in the beginning to stick to this shape, because also most statistical software packages use this kind of shape of raw data matrix. And how does that look like? A raw data matrix has, as all matrices, they have columns and they have lines. And what you always find is that your different variables, they are in the columns, right? Every column is one variable. And the different subjects, they are represented by the different lines. And there is one thing more. The first line in your matrix, the very first line, is not something like a heading or an explanation or whatever. No, leave this all out. Your first line in your raw data matrix is the short names of your variables. And put these names short. You put not your original question or something like this into this. You just give the variable a short name. Yeah. In old data, statistical software packages like SPSS, for instance, these short names were supposed not to be longer than 8 digits, 8 characters, right? So keep it short, okay? So you see an example of a very, very simple raw data matrix in this picture here. Okay? Very often when you write a thesis or whatever, you have to also submit your raw data matrix. And also in the scientific community, you must be able to deliver your raw data matrix along with a description of what these different variables and what these different numbers mean, the coding, for instance. Like we were talking about in the survey specification, we were talking about when we were talking about survey design. Okay, these two things, the simple raw data matrix plus an explanation of what does that mean, what is in the raw data matrix. That's the starting point. So you load that entire thing up into any kind of software that you use for statistical analysis. For a simple statistical analysis, you might use Excel. Okay? I mean, I know many social scientists or hardcore scientists who say, no, you don't use Excel. That's not a scientific program. Why not? I mean, come on, for some basic statistics, you can do this. It's okay. Okay. For some advanced statistics, like multivariate statistical analysis, you, of course, you better use statistical software, statistics software. Okay. So now let's look into descriptive statistics. And I show you here an example. It's a very simple example, and based on the example, we already can explain and understand most statistical measures. So here is a fictitious result on a fictitious question that was asked in a fictitious company in a fictitious employee survey. And the question was, would you recommend a friend to work in our company? Would you recommend a friend to work in our company? It's a classical question. It's a question that we very often use to understand the commitment of people to their employer. Okay, you sometimes have the same question in marketing. Would you recommend a friend to buy this product? Okay, and the answer to this question was yes, mainly yes, partly, mainly no. So you can imagine this, you see this question, and then as a respondent you have to make a choice from yes to no. Okay, so let's say you do this with many people. Okay, so you get one column and you raw data matrix, which is filled with numbers between whatever. So first thing is we code these answers, because in the raw data matrix you don't have the real answers. You don't have, in your raw data matrix, you don't have a yes or mainly yes, because with yes, mainly yes, and so on, you cannot do any statistics. You want to have numbers. Statistics based on numbers. So you have a number. You have to translate these different categories into a number. This is what we name also coding. So let's say, it's arbitrary, say, okay, let's say yes is a 1, and mainly yes is a 2, and a partly is a 3, and so on, until to no is a 5. Okay, so that we can work with numbers and not with words. Okay, that's the basic for doing statistics. Now we can analyze some frequencies, and frequencies are already a statistical measure, so a statistical concept. So frequencies is that you simply indicate how many people in our sample have responded to specific categories. So in our example, 5 people said yes, 23 people said mainly yes, and so on, and 2 people said no. These are frequencies. Yeah. In this case, we name it absolute frequencies. Absolute, because that really tells in absolute terms how many people have responded to that category. Okay, when we sum up all these absolute frequencies, we get a total, in this case, of 55, which tells us 55 people responded to this question. Now we can simply, for every category, we can simply divide the absolute frequency by the total number of respondents, so that we get a relative frequency. Okay, so relative frequency of the category 1, yes, is 0.09. This is simply 5 divided by 55, 0.09. So whenever we use relative frequencies, we do easier when we translate this into percentage by simply multiplying the relative frequency by 100, and then we have percentage. So 0.09 turns into a 9%. Okay, that's simple. So these are relative frequency opposed to absolute frequency. Okay, that's statistics. So when you add up all the relative frequencies in percentage, you come up, you get 100. You all know this, right? Now there is another concept in descriptive statistics that we name cumulative frequency. What is that? Well, the first category was 5. Okay, absolute frequency. Now, with the second category, we can add the first category plus the second. Now we get a 28, which is 5 plus 23. In the third, partly, we simply add the 5 plus the 23 plus the 17 of partly, and we end up with 45. This is cumulative. So is the category, which is it all about, plus all those categories underneath. So, and the last category, in this case, the no, that is probably 55, which is the total number of all respondents, right? You find this concept of cumulative frequency also these days. I produced this series during the Corona crisis. When you have the frequencies of, let's say, all deaths due to COVID-19 every day. So yeah, you have the frequency for every day, and then very often you have the cumulative. Your cumulative frequency means in that particular case, the number of people who died today plus all those people that already have died. So you could also say the cumulative frequency is the number of deaths up to now. Okay? That's cumulative. Okay? And then, of course, you can do the same with the relative frequencies, of course. Now, when you multiply the coding of every category by the absolute frequency and you sum it all up, it's the same like when you sum up all the values that you have. So 5 times 1, 23 times 2, 17 times 3, you sum it all up, you end up with 144. When you have the 144 and you divide this by the total number of respondents, guess what you receive? You receive something that we name the mean, the average, right? Which in this case is 2.62. What does that tell us? That's already a cool number. I mean, it's an average. That reduces 55 numbers into one and tells you what we name in statistics the central tendency. The central tendency of all the numbers. So now you don't have to look at all the numbers. You just look at this number and see, it's 2.62. 2.62, when we look at the coding, okay, that's somewhere between the 2 and the 3, somewhere between the mainly yes and the partly, with a slight tendency towards the partly, because it's more towards the 3 than towards the 2. It's 2.62, right? 2.5 would be exactly in between. It's 2.6, so that looks a little bit more to the partly. Okay, that's already an information that tells us something, and it's really reducing complexity, I would say. So another concept in descriptive statistics is what we name the standard deviation. And I know everything I was sharing with you so far was simple, and you probably already have heard about the frequency. I mean, come on, you know what frequencies are. You also know what relative frequencies are. You might not use this term relative frequency in your daily life, but now you know it, and it was familiar to you. Yeah? You know what that is. Well, you also know what an average is, of course. But what is a standard deviation? In this particular example, the standard deviation is 0.97. We can simply say 1. What does that mean? Standard deviation. Yeah. So let's look at standard deviation, because that's a concept in statistics that is about the variation. It's about the dispersion. It's about to what extent do the values spread somehow around the central tendency, the average, right? So when we look at an example, for instance, intelligence, everything in nature, almost everything in nature, is distributed in a we say normal way. That's why we get this kind of normal curve, right? This bell-shaped curve, right? So when we look at intelligence, for instance, when you measure the intelligence of all people in the world, yeah, you get an average of 100. Intelligence tests are designed this way. They are standardized in that way so that the overall average is always 100. Okay? Okay. So if you have an intelligence quotient of 100, you are exactly in the middle. So here is the other measure, which is standard deviation, which in most intelligence tests is 15. What does that mean? Look at the bell curve. And as I told you, the average is 100. Now we subtract 15 from the average, which is 85. Okay? And then we add 15 to 100, which is 115. So we have a range between 85 and 115. Okay? Simple. Okay? We now can say that when the curve is perfectly normally distributed, that in this range between average minus 1 standard deviation to average plus 1 standard deviation, you find 68% of all cases. Got it? 68% of all cases are in the range between average minus 1 standard deviation, average plus 1 standard deviation. If you got this, you understood the standard deviation. It's easy. 68%. Why 68? Forget it. You don't need to understand, I would say, most of you. 68, that's pretty close to 66. 66 sounds easier. You can better remember 66. 2/3. That's fine. 2/3 are exactly in that range, okay? So let's have another example. There's a student party, okay? And on a student party, there are, let's say, 50 people. I don't know, doesn't matter how many. And now you make a little survey. You ask the people, how old are you, okay? And you find out that the average age on the student party is 20, okay, 20. Nice, cool. So some days later, you go to a wedding and you do the same survey again. You ask the people, how old are you? And the people tell you, and again, the average is 20. Now you can say the average age in both parties is equal. Must have been the same parties, right? Feels pretty similar. Same age in both parties, 20. No, it's not. Because let's assume on a student party, a reasonable standard deviation might be something like 2, right? 2 would mean 2/3 are between 18, 20 minus 2, and 22, 20 plus 2. So standard deviation of 2 sounds pretty reasonable, right? While on a wedding, the standard deviation might be 15. Yeah, because you have 2/3 in the range between 5, 20 minus 15 to 35, 20 plus 15. Because you have all the kids, and you have your aunt, and your parents, and your uncles, and it's kids running around. Okay, some are even younger than 5, and some are even older than 35, of course. Yeah, but 2/3 are somewhere in this middle. So you see, we can also say that the average tells you the age, the central tendency of the age, right, in this regard, in this example. But the standard deviation tells you to what extent this average really reflects the distribution of the different subjects in the group. And the bigger the standard deviation, the more, the broader is the distribution, the more the subjects, they spread it around the central tendency. Okay? So that's the standard deviation. And the thing is that in practice, in daily life and in public news media, we rarely talk about standard deviation. And you will not hear something in CNN in the news that, oh, the standard deviation is this, this. Everybody will say, what is that, standard deviation? But it's an important concept in statistics. Okay? Okay, we use the mean or the average, which is the same. There are different kinds of averages, by the way, but because there is a difference between something which is very important, which is the mean versus the median. The median. The median is also a very important term, I would say, very important. What is the median? Maybe I can explain you the median by telling you a little story. I mean, maybe you are students, you listener, and maybe 10 years after your graduation you meet again, right? So let's say you are male friends, yeah, and I tell you what male friends do when they meet 10 years after graduation. They will make this game of who has the biggest car here now, who has the biggest house, who has the prettiest girlfriend, and so on. It's a man's game, you know. And so let's be very stereotypic and let's say 4 friends, they meet after graduation. So one of the four is late, so the three of them already meet at the bar where they always met when they were students. They have some beer and okay, the game starts and the question, hey, what do you earn? And the first says, well, 100,000 in a year, and the other says, oh wow, 100,000. Me too, 100,000. And the other is also 100,000. We all earn 100,000. Wow, that's pretty cool. And now comes the fourth friend into the bar. He took a while because he had to find a parking a lot for his Ferrari. You also already could listen to him from the distance, and now this friend comes in having a beer. Asks, hey, how much do you earn? 1 million. 1 million. Wow. So what's the average? 100 plus 100 plus 100,000 plus a million is something around 1,300,000 divided by 4 is I have to calculate 300,000 some things, okay? And then you tell the barkeep, hey, we on average earn more than 300,000. No, you don't. Most don't. That would be a misleading information, right? Absolutely. So the average really changes when the rich come in, but the median doesn't. What is the median? The median is a simple concept in statistics. You look at all the cases, you look at all the values, you put them into a row from the lowest to the highest, for instance, with regards to compensation or whatever, right? Age, whatever. You put them in a row, and then you try to split the group into two halves. And that value that splits the group into two halves, that's the median. Okay? That's the median. So the median is very useful when you have a not normally distributed curve, right? So the median is, as I said, the point that splits a group into two halves. There are 50% that are more higher than the median, and there are 50% lower than the median. So when you have a curve which is more flat to the positive end, and when you have some extremes, as you have, for instance, with salary, when you look at the salary distribution in society, it's not normally distributed. You always have very few, very, very rich people. That's why when we look at the descriptive statistic about salary, you never use the average, because those incredibly rich guys, they will pull the average towards the positive end. So we better use the mean. The mean does not pull to the positive end. That stays there. Okay? So when you look at these two curves, with a normal distributed curve, the mean is equal to the average, because it's simply the middle. Yeah? Okay? It's because this curve is symmetrical, right? But when it's not, you can say the mean is pulled more towards the extreme ends, while the mean stays more on the left side in with regards to our example here. Okay? So when you let's have an example. I used to ask this in an exam in human resource management also. Let's assume you have a company of 100 people, right? And the people, they on average earn 50,000 euro, dollar a year, on average, let's say 50,000. And now you hire somebody who earns incredibly much. One person, you hire one person who earns 1 million in a year. How does that change the average? It changes the average, right? How does it change the median? Not at all. Or just to a minimum, right? So the median is a good statistical concept that is robust against outliers. And that's why we use it, okay? It's important. Yeah. So when you add an outlier to a distribution, the mean will be affected and the median won't. Okay? So what we also do very often in descriptive statistics is that we try to illustrate or to present our frequencies in certain graphs. And a nice example, for instance, is the histogram. The histogram, you see one here. You might use the relative or the absolute frequency. It will look the same. And you have bars. It's a bar chart, a histogram, a nice way. When you have relative frequencies, you also can use a ring chart, for instance, a pie chart or something. But you only use ring charts or pie charts when the frequencies really sum up to 200%, so relative frequencies. With absolute frequencies, a ring chart would not make any sense, right? This is a good way of doing things. And now, at the end of this episode, I would like to add something which is essential, and I only can explain it now because we already were talking about it, about some concepts we need now. When you do your analysis, yeah, and you have your raw data matrix, which is the starting point. I mean, that's your material that you use for your statistical analysis. The first thing is that you have to prepare your data, right? And some fundamental steps for preparing your data is that you exclude non-valid values. That's one point. So I would like to share with you now a little bit of checklist, yeah, that you can work on when you prepare your data. Take out non-valid values. Why is that? I mean, some values that you find are really not valid. Yeah, really not. I do not talk about missing value, I talk about non-valid values. So a nice example is, for instance, when you ask people, how old are you? And somebody says, 33,678. I say, yeah, my friend, you know, that's a joke. Sorry, you take this out. Yeah, there are all sorts of data where you instantly see it's not valid. Sorry. Yeah. It's sometimes difficult, but just I don't want to go too deep into this. You look at the data and say, could that be? And the other thing is outliers. Sometimes you really have outliers. Let's assume you do a study about, I don't know, sports. Okay, sports. You look at the performance of, let's say, some youth, yeah, in golf. Yeah, you do a study about their performance in golf, and now you have somebody in your sample who was a national champion. Incredibly good. So much better than all the others. Take this guy out. Because when you leave outliers in your sample, it could be that this one outlier will determine the overall results. We find this very often with correlation. When you have an outlier in a correlation, that can turn the results upside down. So take out outliers. So outlier is defined into statistical term. And here's a concept that I have to explain. It's the interquartile range. Before you try to understand this, you have to understand what is a quartile. What is a quartile? If you have understand the median, then you also understand the quartile. What is a quartile? You have three quartiles. Yeah? The first, the second, and the third. And the second is equal to the median. And the three quartiles, they split the sample into 4 equal groups. You know? The median did split the group into 2 halves, the quartile into 4 equal groups. So the first quartile is the value that splits the group into 25% and the upper 75%. That's the first quartile. The second quartile equal to the median, 50%, 50%. And the third quartile is 75, 25. Okay, this is the quartile. Now what is the interquartile range? The interquartile range is the range between the first quartile and the third quartile. Okay? So, and if a value is higher than the third quartile, more than 1.5 times the interquartile range, higher than the third quartile, then it's an outlier. Okay? So you don't have to understand this by heart, but what you take home is an outlier is defined in statistical terms. It's very, 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 very extreme value you better take out. And there's something else that you very often might do. before you start analyzing your data. It's what we name a set transformation, you might have data of all different sorts. Some data, they rank from 0 to 10, the other rank from 0 to 100, the other from 1 to 5, or whatever. So you have different sorts of data, and you want to compare this different data, these different variables. And you want to compare it in a way every variable has 0 as an average and 1 as a standard deviation. So you standardize all the variables so that they all have the same average and the same standard deviation. Sometimes that's reasonable, especially when you add different values up for calculating an overall index, for instance, right? So set transformation, that's something that you might do. It's a very simple formula. Yeah. From the value you have, you subtract the average and divide this by the standard deviation. Then you receive a mean of from 0 and a standard deviation of 1. Okay, that's very simple. Also, sometimes you need to change the polarity of items. We were talking about polarities when we were talking about survey design. When you have a question that goes from yes to no, sometimes yes is the positive result and sometimes no is the positive result. So whatever you measure, you should make sure that all your questions, they look all in the same direction, so that yes always means maybe good leadership quality and no means bad leadership quality. But sometimes it's upside down, depending on how you ask. So you have to make sure that all items have the same polarity. For some reason that makes sense. And sometimes you want to calculate an index. An index is an overall total score. When you have multiple items, multiple questions that you sum up to an overall score, as you would do for any kind of test, for instance. Yeah, we were talking about this when we were talking about testing, right? If you don't remember, go back to this particular episode. This is also something that you very often do when you prepare your data for analysis. You sum up the values of different variables and have an overall value that in the end you use for your final analysis. Okay, so I would leave it to this now. That was descriptive statistics, and there's much more about descriptive statistics, but these are the things that you really take home. Okay, now you have understood what is the mean, what is the median. You understood what is the standard deviation, the various kinds of frequencies, quartile, yeah, all these things. So that should be enough for the moment, okay? And in the next episode, we will look at bivariate statistic. It's about to analyze the relation between two variables. I mean, up to now, we were just talking about the analysis of one single variable, central tendency and dispersion. In the next time, we talk about how you can analyze the relation between two variables. Okay? So, cool. Thank you for watching and listening, and see you next time.